So good afternoon everyone. Today we have the NVMe Management Interface, NVMe Drivers, SPDK updates, and then we have the NVMe over the Fabrics updates. So let me invite Mr. Myron from Intel and Austin from Dell for the NVMe-MI interface.
All right. Good afternoon. My name is Austin Bolin, and over here we have Myron Lowen, and today we're going to talk about the NVMe Management Interface. So for the agenda, a lot of these items we've covered in detail before, so I'm just going to do a quick overview and touch on the highlights for most of these. But for those that are interested, there's some links at the end of this presentation that have a lot more detail if you want to look that up. One of the topics that we haven't covered in much detail before is the topic on managing multi-NVM subsystem devices, which is a proposal that Myron wrote. So he'll do a deeper dive on that topic. So here we have an overview of the NVM Express organization. There's a variety of different work groups that work on various NVMe-related topics. This presentation is really going to focus on the management interface work group. This is a work group that publishes the NVMe management interface specification. And this is really a complement to the NVMe base specification, which is put out by the technical work group, but it really focuses on the management aspects related to NVMe. Okay, so we put out the first revision of the MI spec back in the first revision of MI 1.0A back in 2015, and then we put a small update out in 2017, which is the 1.0A spec. And so if you're doing anything with MI right now, that's the latest version, so that's the one you want to be using. Now, in parallel with 1.0A, we started to work on 1.1, and in the lower right, we have a few of the anchor features that we've been working on. A couple of these, the Inband mechanism and the Enclosure Management, those are ratified and they're incorporated into the latest 1.1 draft specification. So ratified here just means they're complete, they've been reviewed and approved by the NVMe organization, and member companies are free to start implementing them. Now we also worked on several other smaller features, and we made some errata fixes. Those are all ratified and incorporated into the 1.1 spec as well. And really the only thing we're still working on right now is we're wrapping up the multi-NVM subsystem device support, which should be done imminently. Once that's done, we'll go through all the review processes and hope to have the 1.1 spec out by the end of this year. Now we have a lot of support for MI in the ecosystem. There's commercial test equipment available from a number of vendors to help people test and debug their MI solutions. We have an official compliance test suite and integrators list from the UNH IOL. And we have lots of products available in the market today that you can buy. There's servers that support MI, and there's drives from multiple drive vendors that support MI as well. So I wanted to do a quick recap on what the management interface is in the 1.0A spec, and then we kind of illustrate how it's changing in 1.1. So the soundbite that sums it up here is that it's a programming interface that allows out-of-band management of an NVMe storage device field replaceable unit, or a FRU. So management here involves things like taking inventory of the devices in a system, being able to monitor those devices, things like their health and their temperature and so forth, being able to configure those devices and update their firmware. That's all going to roll forward into the 1.1 specification. And in addition, 1.0 is really limited only to out-of-band management, and it's really limited to managing NVMe devices with a single NVM subsystem. You'll still be able to do both of those in 1.1, but we're going to extend those, and we'll talk about how in the coming slides. Now, as I mentioned, 1.0a is really focused on out-of-band management. In this context, out-of-band means independent of the host operating system. So in a server, you typically have your host processor running your host operating system, and then you'd connect NVMe devices to that via the PCI Express bus. And then you'd have a baseboard management controller, or BMC. And in 1.0a, this BMC can communicate and manage NVMe devices out of band, independent of the host operating system, either via SM bus, as shown on the right, or via PCI Express vendor-defined messages, as shown on the left. Here we have the out-of-band protocol layering used by MI. MI was built as a layer that sits on top of the Management Component Transport Protocol, or MCTP. This is an existing spec that's published by the Distributed Management Task Force. MCTP has bindings to several different physical layers, and MI runs on two of those, PCI Express and SM bus, as we saw on the previous slide. Now, in the NVM Express base specification, they're really focused on a device driver that's talking to an individual NVMe controller. But an NVMe device can have multiple controllers on it. But for management, in addition to being able to talk to individual controllers, we really want to manage the thing at the physical device level, or the FRU level. And in 1.0a, we refer to these FRUs as an NVMe storage device. An NVMe storage device in 1.0a is defined as something that has one and only one NVM subsystem. It's got one or more PCIe ports. It's got vital product data, and it's got an optional SM bus or I2C interface. Here we have a couple examples. On the left, we have a single-ported add-in card, and on the right, we have a dual-ported U.2 drive. Okay, so one of the anchor features for 1.1 that we're adding is a proposal that I wrote to add in support for Inband Management interface. So as we talked about before, out-of-band management is independent of the host operating system. And by contrast, in-band management is dependent on the host operating system. And so there on the left in red, we have the in-band path that goes from the NVMe driver in the host operating system down to the NVMe device. That interface is defined by the NVM Express base specification, which is put out by the technical work group. And they have a few different command sets they support, the NVM command set and the admin command set. And so the way that we're adding in support for Inband MI is we actually created two new NVMe admin commands. And these are really just wrapper commands that allow us to tunnel MI in-band. They're the MI send command, which allows us to wrap up MI commands that send data from the host to the device, so similar to a write operation. And NVMe-MI receive, which is used to wrap up MI commands that send data from the device to the host, similar to a read operation. Now, the benefit of doing this is this allows us to execute MI commands in-band from the host operating system or from a management application within the host operating system that we would otherwise only be able to execute out-of-band from a BMC. So this would involve things like being able to manage NVMe at the FRU level, reading the vital product data from an NVMe device, and doing NVMe Enclosure Management. The in-band support also lays down the plumbing to be able to tunnel MI over NVMe over fabrics. This isn't an official work item right now, but folks have expressed interest in it, so it may be formalized in the future. Another anchor feature we have for 1.1 is a proposal written by Peter Nufrick, which is for NVMe Enclosure Management. An NVMe enclosure consists of NVMe storage devices, and also a lot of different elements to support those NVMe devices like fans and power supplies and status LEDs and so forth. These elements are the same types of elements that you'd find in a SCSI enclosure. And as such, we leverage SCSI enclosure services to do the NVMe Enclosure Management. SES is a standard that's published by the T10 organization, and it's widely used for SCSI enclosure management today in the industry. The way that we're going to take advantage of SES is by tunneling the SES data structures over MI using two new MI commands, SES send and SES receive, which are equivalent to the SCSI commands diagnostic send and diagnostic receive result. With that, I'm going to turn it over to Myron to talk about the third anchor feature for 1.1, which is the multi-NVM subsystem device management. Thank you.
Thanks, Austin. Yeah, that was a great overview of many of the things that we're doing for 1.1. I'm just going to focus on the one now for multi-subsystem. So if we look back, Austin already had this, so I'm not going to go into detail on this side, but this is what 1.08 storage devices used to look like. Then along came all these new devices that people are building, and so we have to play catch up. On the left side, you see the M.2 carrier board that has two M.2s plugged in with a switch. On the right side, you see a Facebook example with 4 M.2 drives and an add-in card form factor. Those ones use bifurcations. They don't have a PCIe switch. So none of this stuff has a good way to represent in our VPD data, and it doesn't have a good way. Bifurcation is really a problem where storage is running ahead of the PCIe industry, and we came up with some proposals here that we think will be applicable elsewhere. And so that's what this presentation here is on. So if we look at the picture here, this is basically you have an SM bus connecting a VPD data source and a subsystem on the drive. Then we come up with all this new stuff. So that previous picture was what 1.0 has. All this new stuff needs a way to be described in the VPD so that when the host is looking at the drive, it can find out what's attached and how to talk to each of these pieces. So here what we see is that there's two different ways. The picture on the left uses ARP. The picture on the right uses a MUX. We're supporting either way to talk to the drive. And we also have come up with some new UDID types to connect stuff like the MUXes. A MUX with ARP has to be able to be associated with that drive because there's no other physical connection between the two. And this is more of the same in the interest of time. We'll just skip ahead here. So what we needed was a language to describe what this drive was. And this is kind of what the language is. The language has these components called elements. There's a host PCIe port. There's your host power, your PCIe switch, SM bus MUX. All of these different elements must be interconnected with each other. And we did that with this fancy table here. Here's a single port example. You don't need to read all the details. But what we basically have here is that there's these elements. You see element 0, 1, 2 on the left side, and each element has a variable number of parameters, and those parameters describe the connections between different elements. You can see here that this is very efficient size-wise. This particular drive uses 35 bytes of a 256-byte EEPROM to describe that drive. And then we did some more fancy examples, and here we see on the left side, you see a switch with 2 subsystems on a drive. This is something that we couldn't do prior to 1.1 in the spec. These products exist. We needed a way to describe them. And then the picture on the right is something that it's conceivable, but nobody's built anything like this. This would be more like a universal backplane where you have a bunch of the center part with the switches would connect a whole bunch of dual-ported drives to 2 hosts. And we just were testing our language, and we can describe either of these with 82 bytes or 78 bytes. So these are kind of our use cases. These are described in the TP spec. They'll be part of the appendix, and you can actually use these examples to create your own VPD data. So in summary, 1.0 is gaining marketplace acceptance. 1.1 is near completion, and we're starting to put some forward-looking thought into what the features will be for 1.2. And Like Austin said earlier, at the end of the slide deck, there's some 2 slides on reference material that you guys can look up on your own time. And the floor is open to any questions if we have time.
We have time.
Okay. Any questions on MI? I'll get Austin to stand up if it applies to him.
So I have a question for both of you. So what is next in the MI coming up? Like, do you see next revision coming up soon, major revision coming up soon, or you have anything major that's coming up?
I'll let Austin answer that too, but we don't have release dates that we're targeting.
Okay.
So we just accumulate a backlog of technical material that we don't have a way to describe.
Okay.
And when as that comes up and we present it, or people bring TPs to the organization, we agree on that that's something we should proceed with.
Okay.
Did you have some things that you wanted to?
So what are the major TPs that are not part of the existing public release?
So the difficulty there is that none of them have been approved.
I see. Okay.
So they will all just be thoughts at this point.
Any preview into what's coming up?
Oh, stuff around being able to get better bandwidth efficiency on the backplane.
Okay.
Like sharing time slots with different slots.
Okay.
Did you have
any interesting TPs?
No, we're trying to wrap up 1.1 now, and so folks have things they want to do in the future. Now's the time to bring those ideas forward.
Great. All right. Thank you, guys. Thank you very much. Myron from Intel, you have a question?
Yeah, there certainly is LED control built into this stuff. Okay. So you can use LED control, but you'd have, in a gaming machine, you typically don't have a board management computer or controller, which is what controls all of this stuff. This isn't done so much by the OS. The OS has that path that we talked about earlier about being able to do the Inband MI commands, but the out-of-band with SMBus or VPDs over PCIe traffic, that would typically be done by a BMC controller.
Okay, I have another question, 2 more questions actually. So what is the adaptation and maturity in the industry as of today for the NVMe-MI? So how mature it is? Like, is it widely adopted by all the OEMs and pretty much all the ODMs and the device vendors and stuff like that?
So 1.0A is widely accepted. We've had 3 plugfests now. For sure, 2 plugfests, or like the where they do all the UNC testing to make sure everybody's compatible with each other.
Okay.
And there's a number of drives that are on their website that are on the if you go to NVMe website, you can find them there. And I think there's 8 to 10 drives, something like that. And those ones are all compatible. There's more that aren't even on that list. There's quite a few.
Coming on to the LED management, you said that it's done through BMC.
There's many different ways to manage LEDs. So one of the ways is through these commands that we just talked about, and that would be through the enclosure. There's also the white box method that we've talked about. We actually handed off that information to the PCIe SIG, which then ran with it and standardized it instead of us. So they have a more in-band way to do it. The enclosures, that's all brand new technology. So the spec is like, we've agreed to what the spec is, but it hasn't been published for the real world to see yet. And so once they see that, then the products will start to follow. Yeah, so I'll summarize your question. If I'm completely wrong, just let me know. The problem is really that SMBus is a very low bandwidth protocol, and sharing it across a whole bunch of drives that have some latencies and time between them. How do we get that efficiency up so we can scale across a large number of drives? And so what we've found is that probably the limit peaks out around 32 drives on a SMBus segment. As far as timing to get back in a reasonable time. The main urgency to get back to every drive is really to check the temperature and keep the fan speed, those closed loop algorithms going. The other stuff isn't quite as timing sensitive. And that 32 drives you can easily accomplish in a 4-second window. So, yeah, and we rewrote the spec so either method is possible. You could use ARP or muxes to communicate with them all. Both of them, I think, will hit the 4-second window without any trouble. What's even more efficient is to use ARP with muxes. Not more efficient, it's as efficient bandwidth-wise as ARP, but it gives you the reliability of muxes. Because the mux, you just turn on all the channels at once, and then you can turn off a channel if there's an offender you're trying to get rid of.
All right, thank you. Give a big hands up to Myron and Austin. So these two gentlemen are the ones actually contributed to the specification a lot. So thanks again, both of you. And the next part is the NVMe drivers update. So we have the UEFI drivers, NVMe or Fabrics update, a little bit for the driver session. And also I have talking about the Linux drivers, and then we have the Leap about the Microsoft drivers, and after that we have Sarge Jain about the VMware drivers. Then we have Jim talking about the SPDK. So let me briefly give a quick update, then I'll hand over to the next speaker. So the NVMe driver ecosystem is pretty much complete now, right? We have the Microsoft inbox drivers, we have the Linux drivers, VMware, and UEFI. So if you go to nvmexpress.org website, you will see the drivers homepage. You can download the drivers from there. And most of them are inbox anyway. So even the UEFI drivers, they come with the systems. So you don't have to download anything specially. So what's new? Basically, we have a very stable UEFI drivers on the Intel platforms for a very long time. And I did porting for most of it actually, both on the NVMe SSD side and also on the platform side. So now we have the ARM support also on the UEFI drivers, and it pretty much boots, NVMe boots on the ARM platforms too. We have the complete coverage. And I have a slide on NVMe over Fabrics, and thanks to Nishant from my company, Marvell. So NVMe over Fabrics driver support, we have NVMe over RDMA, Fiber Channel, TCP, and IWAP. So some of the code is contributed by KVM Marvell team to the upstream Linux, and thanks to those guys. And that's the update. Any questions on the UEFI drivers or the Fabrics driver side of it? Okay. If not, I will move on to the next presenter, Mr. Leaproyd. So he's the hardware program manager, and he has been doing this for a very long time. Thank you.
Okay, so pretty short presentation here. Don't blink or you'll miss it. I just want to kind of talk about some of the things that we put in over the last year, and then some thoughts for the future. So, and there's exactly that. And if the nomenclature here, RS4 and RS5. RS4 was the release that happened this spring. RS5 is what's coming up in this fall. As people are probably pretty well aware now, we've gotten to the model, and we're doing pretty good around maybe a 6-month cadence or so, where we do a new release of Windows and kind of get that going and rolling along, much more agile, so to speak. So these two that we actually did in RS4, they're not specifically NVMe features per se, but they were applied to the NVMe driver in the case of the DMA remapping, this is how we protect from drive-by attacks through DMA. So you could think of somebody pulling something in on a Thunderbolt bus and trying to then snoop DMA space, pretending to be a device. And so with DMA remapping support in all our different storage and PCI drivers, we block all that. So that's a security measure. And the F-state stair-stepping, this is really how we do very fine-grained power state mapping for both active and non-active power within the device. You can think of things like in our connected standby systems, somebody's playing music. So the music's going and you're accessing the drive every once in a while to get some more music, but the screen's off. And so we don't need the absolute bandwidth at that point. We can go to a lower power state that the drive can satisfy and just kind of trickle out stuff to the player as we need it. And a few more things in RS5. Asynchronous event notification. This is basically for things like Fabrics, where you have remote devices and where namespaces come and go off the system where I don't see them in the plug and play. So if there's no notifications that they're coming and going. It has to be done through a band mechanism in the driver itself. So that'll be there that helps with fabrics, that helps with things like virtualization. So as virtual devices come and go, those will get picked up through this mechanism. Device telemetry. This is something we think is really important. We think the drive guys hopefully will be on board with this. This is a mechanism where from the spec there's a ability for us to give a command. The command gives a payload of private data that's maybe encrypted and compressed and all that good stuff that we then get back to Microsoft, and we can see whose it is, and then we can give it to those drive manufacturers so that we can start to process their problems in the field very quickly because they can have their debug stuff back to them in a timely manner. And of course, the new stuff for the extended log pages, where the ability to have very large log pages and be able to get very large data sets out of them. We're also supporting that. And in the future, so obviously not plan of record, do not pass go, safe harbor, all that. These are just thoughts. Some of these are maybe more concrete than others, but still the timing of when they might go in is TBD. So what we call D3, so basically the ability to turn the device off in its lowest power state, just have it sit there, everything's off, and we save the most power. Doing some more stuff around thermal management. Today we take in the events when there's a thermal event on the drive and we mark that, but we don't really do much management itself other than let the drive do it. So we want to be able to take more control of that, especially in space constrained designs where we're actually getting heat input from temperature sensors around the laptop, not just from the device itself, so that we can then manage the thermal power or thermal and the power across the whole system as a whole. Support for sets. Sets have been there now for a little while. They're in 1.3. We want to be able to take advantage of those in certain use cases. Endurance groups is the same kind of thing, and namespace management. So that we're building these blocks up to have more fine-grained ability to take a device, chop it up in sundry and interesting ways, and give it off to either a guest VM or dividing it up on some sort of different form factors for client devices. So that's it.
So we have some more time. So any questions? Yeah, there's one question.
Can you comment on NVMe over Fabric inbox support?
So at this point, there is no plans to do an inbox driver for NVMe over Fabrics. That's mostly due to the focus and timing. As you know, one of our probably primary customers is a thing called Azure. Azure is not really moving towards Fabrics at this point. It's all aggregated, it's all hyperconverged storage. So we just don't have the bandwidth to do it right now.
I had heard rumors there was some development going on.
Yeah, I think different people, different groups have kind of been doing some kind of percolating and stuff, and we're more than happy to help out with that in any way we can. There's been some talk about maybe actually bringing it into the NVMe group and doing a standard, open source Windows driver, and we would again help out with that. Not that we, take it in box, maybe not, all that.
That would help.
Yeah.
So great question. So any other questions?
Good question. It would have to be basically which binding we chose to do first would probably be based on the need and the ecosystem and the scope. So probably RDMA to start. But part of the process would be we need to divide the Windows driver kind of like we've done in the spec, pull out that PCI-ness into its own kind of thing. There's the NVMe transport stuff, PCI transport stuff. Divide that out in the driver and allow different things to get shoved in as we built them and put them together. Make sense? Yeah.
Sure. Your best guess, not happening.
Yeah, no PR. No PR right now. Not happening.
So any time you have for these future items that?
Yeah, as I say, it's all kind of soft. I mean, obviously, we have the 6 month cadence now. Some of these things will definitely come in the next 6 months. Some probably won't. I don't know quite yet. But,
Okay.
yeah, but you can see, it's more in 12 months, more in 18 months, and then we'll have other things that we want to do on top of this. There's just some brand new things that we're thinking around, like a zoned interface to NVMe, just like ZAC CBC and SMR drives, that sort of thing.
Great, that's good. So, one last question. Anybody else has any questions? No. Okay. See your time. So go ahead. Yeah.
I would like to ask, just like you said, because you talk about these future features, so is there any technical documents or proposal documents available, currently available on the website now?
Yeah, not now. That's to say, we usually, because they are futures, we don't tend to put it in on the website in hard writing because it's a future. Usually, what it is if this is something of interest and you're an IHV, we're usually trying to have conversations with the different IHVs around what this means for their device and how can we get samples of stuff that supports it and that sort of thing. So.
Okay, great. Thank you, Lee. I appreciate it. Yeah. So our next presenter is Mr. Dave Minton from Intel.
Hello, everyone. I'm going to do a update on Linux drivers. And Linux drivers are a little bit different than some of the other OSs in the fact that there's two parts to the Linux driver set. One being the host driver, which now is has been a multi-transport driver now for a couple of years, and then there's the target driver, which which is on the backside of some of the NVMe Fabric targets. So as I show some of these updates, I'll try to point out like which ones were done for the for the PCIe, which one were done for the fabrics, and which one was done for NVMe architecture in general. Because that's sort of the way the Linux driver is laid out. So this is I put this together sort of as what's happened over the last year in the Linux NVMe driver world, and it really sort of marches along with the various releases of the Linux kernel. When patches are submitted, they're collected, and this specific version will have very specific features for this driver that they want to get in for that. So if you look at just in summary, like for instance, we started at 4.13, now we're going into 4.19. Along the way, some of the adding functionality had to do with CMB, controller memory buffer early on, in October, namespace ID all for the flush. Some firmware activate, without reset. Next, 4.15 SGLs. Everybody's been screaming for SGLs for a long time. Okay, we've got SGLs now. Native multipath, which is, if you want some interesting reading on multipath in Linux, this is sort of an interesting area. User level notifications, and then just, miscellaneous fixes. And then we have a span, I was trying to figure out between, 4.15 and 4.17, but really a lot of it was, just stability patches, nothing specific as far as a big functional patch. And then in 4.18, they had something called file back namespaces. This is for the target. So imagine a target that, is presenting out an NVMe namespace to a host. On the backside of that target, was typically a block device. Now you can have a file device on the back end that the namespace maps to on the target. In 4.19, there was a request to, actually to put bigger in-capsule data, for larger IOs. And in-capsule data has to do with data that's sent, from the host without the target requesting it. So for what it does is it's a latency reduction across certain types of transport. So that was added up to 16K in 4.19. Asynchronous event notifications was added. Buffered IO that was put in place to help with the file back namespaces. And then trace points. I think one of the maintainers, I think I think Keith put that in sort of as like one of his big last items with the, fixed trace points. Looking towards the next 12 months, there again, this is not like, anything that's set in stone, but really it's more around what parts of the specifications are solidifying either in a whole new release like a 1.1 fabrics release or a technical proposal that's been ratified and was public. Some of these have to do, the big item for 1.1 is the TCP transport, which expect as soon as that is ratified, you're going to see it the next day. Because it's actually, we have it up and running in a private repo with the working group, but it's been running for a year. So I think it's really just more a matter of getting this. Once that specification, all the everything grammar is correct and everything else, then that goes out. Discovery log, asynchronous notification. This has to do with sort of enhanced discovery that's being put in 1.1, where targets can be discovered, it's more automatically as opposed to, having to manually go out and find the targets. Flow control negotiation, authentication, transport, ASGLs and error codes. These are all items that you'll see in TPs. And I stole, some of this slide from another NVMe talk. As far as the NVMe host core and PCIe transport functionality, based on some of the 1.1 or 1.4 features that are happening, some asynchronous namespace access. This applies to both PCIe and fabrics. Persistent memory regions are really more for PCIe transport. Determinism and NVM sets, that were mentioned before. This is common across both PCIe and the fabrics. And then host memory buffers more for the PCIe. I updated this slide. I think I did this slide maybe a couple of years ago, and now I got to add a couple more transports into it. Like when we first did this, it was PCIe and RDMA. Now we get fiber channel, and then we got TCP coming in as the fourth transport to the host driver, which I think is pretty cool. It's actually, the host driver is set up very cleanly to be able to add a transport very readily. I want to say the TCP, I know the person, that worked on this, had it actually sort of integrated into both host and target in a day. Okay. Yeah, so this is, if you go back and look at this diagram, you can go to the source code and sort of see the various pieces of what the host driver looks like. Looking at the target side, like I said, what's different in this diagram are the additional transports, and also this file-backed namespaces that were added recently. Put together a list of references, if you want to go and see, for instance, what are the latest TPs that have been ratified. They're up on the MM-Express webpage. If you want to go look at the Linux driver sources, go to the kernel.org, for the mainline and stable. If you really want to get into it and want to see the day-to-day activity, with the maintainers and the folks adding stuff, go to the Linux reflector and, probably put it in a different folder, because it's, sometimes it's like, 50 emails a day or something like that, but that's really where most of the work happens, on a day-to-day basis. There's an internal working group, which I chair in NVMe org. If you're a member and you're a member of this working group, what we do is we develop all the drivers, mostly fabric drivers, in advance of the specifications being, done, so that we actually have working versions of this for, many, many months before the specification's done. And, as a member and as a member of this group, you would have access to that, sort of early access.
Any questions on the Linux driver front?
Oh, like the timeline one? Yeah, actually, that was Git pulls. I just basically went back and looked at the Git pulls for each of the various releases and said, okay, what were the big features that were put into that release? So those are actually, when it was available in the code. Yeah, I would have said months ago, but it's any time. Yeah, it's basically, in a phase of completeness and more of in a wordsmithing phase. It's technically complete, going through word phasing, so that when it gets put in the spec, we're not having to do errata around the wording and things like that. Sort of the phase it's at. The ones that we use internally are actually, we base ours based off of some distros, so, like for instance, a Red Hat distro that we put the NVMe drivers into, I want to say it was like, I have to think about that for a minute. Is it 4.3 or something like that? It was the version we put it in. That's what we use internally, unless we're doing something specific for a feature that we want to test out. That's your safest bet, is to pick a distro that has, especially for the PCIe driver with base functionality. Unless you want one of these features that I pointed out, that's your safest bet.
So there's no major stability issues in the earlier versions that were fixed or any of those up there?
I wouldn't say they're stability issues per se. I would say that's probably not the case. But I think it's more of a functionality. Does it have this certain functionality? I think there's maybe some reset things, that were fixed. You have to sort of go along and say, okay, which pieces, because that's sort of what the distro guys do, right? They're going to look at this stuff. They're going to pull the patches that make it the most stable. And a functionality patch is sometimes a negotiation. Say, my drive has this feature. I want this in, your release, or something like that. Versus, okay, this is going to make the system unstable. No question asked. That gets pulled. So you sort of have to look at, those type of differences.
Thank you, Dave. It's an amazing progress on the Linux driver side. It's good to see that. So our next speaker is Mr. Sudhanshu Jain from VMware.
Good afternoon. My name is Sudh Jain. I'm part of the VMware's product management team focused on a lot of new technologies for VMware. My focus is primarily on NVMe, NVM, persistent memory, RDMA, and a lot of SmartNIC effort which we drive internally. So basically, as far as the NVMe is concerned in the VMware, we have been working on it for many, many years now. So I will go and talk about a little bit on what we have done in vSphere 6.7 and a little bit on the future direction. Again, the disclaimer, future direction is no POR, but something we have been working actively, and I would like to come back here in this forum and share it more in future. So as far as the NVMe is concerned, basically inside VMware, it's a big focus, and it's a focus at multiple layer. As you know, how many of you are VMware partner or VMware customer or who impact? If you can show me a show of hands. Some. I know some who are not raising their hand. That's fine. Okay. So basically, we have the driver, which is the layer we are going to talk about. That's the focus. But in addition to that, there's a lot of impact of NVMe on the core storage itself, and beyond that in the virtualization layer, where we run our guest operating system, whether it's been Linux or Windows, or for that matter, any other OS. So what we have been doing it in NVMe front, we've been working on almost every layer for that matter. Basically, we have been in vSphere 6.5, which was released, I will say, about 20 months back or so, or 18 months back. And that has been, has a very rich ecosystem. It's been out there for some time. And we have almost, I will say, all the big vendors, or rather most of the vendors, NVMe products are certified on our driver for that matter. And we are speccing it for 1.1 something at the 6.5. And what we have done is, what's new for this particular discussion, we introduced vSphere 6.7, and we introduced it earlier this year. And that's came out with, we have the spec. We align it more with the 1.21 spec. We introduced a lot of new exciting features as well as improve the performance, make some manageability also improved on that front. For example, we introduced unmapped support. We introduced also 4K on the driver front. And also something we have done big in the core storage for that matter, we introduced a new plugin. Basically, it's a little bit more optimized plugin than what we have a default plugin, what we call NMP. That's multipath plugin. We have a default one. Now we have introduced what we call internally high performance plugin. It's mainly targeted to NVMe products, and that's something is giving us a lot of improved performance as well. Moving forward, I think on the virtual device as well, we have a virtual device emulation at the virtual layer, and that gives us a capability to run the guest operating system with the native NVMe driver from Linux and Windows So all the good thing you heard from Linux and Windows, you can natively run on top of VMware with our device simulation. So that basically gives us, so we don't have to have our own driver on the virtualization layer. Virtualization layer, we leverage the driver from Windows and Linux, but we emulate the NVMe spec 1.0e at this time in 6.7. We're going to go and move forward in future to rev that spec as well. But in 6.7, we have done the optimization on that front as well, on performance improvement, async support, or the virtualization layer. So that's a lot of good, exciting work we have done in 6.7. And moving forward, future direction, again, disclaimer, it's not something we have any POR at this time. But if you come to VMworld, which is later this month, you will hear a lot more about some of the future work in live demos and some of the even tech talks as well. So we are focusing on NVMe Fabric. I think that's a big buzzword in this conference as well. And we continue to invest in that area. Also, basically, as you know, traditionally VMware, or rather for that matter, any OS is a SCSI stack, but we are making it more end-to-end NVMe stack. So that's a big focus from the core storage perspective, and we'll continue to invest in that area as well. We want to get to end-to-end NVMe where there's no SCSI translation happening, and we get end-to-end NVMe. And also on the virtualization layer as well, we are going to rev up the spec, and we will go and do the virtualization layer as well, 4K. We do support 4K at the driver layer and at the kernel, but at the virtualization layer, we still are 512, and we are going to go towards the 4K as well in future. So what I mentioned about the high performance plugin, this is something, a stepping stone towards our next generation storage stack, and we are seeing a lot of good results about it already. So if you are interested, you can use this. It's a new plugin. It's not default, but you can enable that. And once you enable it, especially for NVMe drives, you will see a significant improvement in the performance as well. So that's what's on the 6.7. Basically, I don't have much to talk about the future, but I'll give you a glimpse of what we have been working in-house in our labs as we speak. So we are going towards, as you said, NVMe Fabric kind of model, where NVMe layer should be able to do and work with multiple transport. Not very different than what you saw from the Linux presentation. We are pretty much in line as far as overall architecture goes. No secret sauce here, but that's a focus. We like to go and make sure, as and when the industry adopt NVMe Fabric, we are ready. We have multiple transport we want to go and make it available. We are not going to go and bet on one versus the other. As and when the industry look for something, we'll support that. So that's the area we'll continue to invest, and I look forward to see many of you at VMworld, and see you will be able to see some of these demos in live over there. Also, basically, all that, as Uma mentioned, it's available on NVMe or Fabric org, and also on our website. All the products certified, available on a single point. We call it VMware Compatibility Guide. You can go there and see. You can download our drivers. You can see all the NVMe controller which are certified with our product. That's pretty much it from my side. Thank you.
So any questions to Satyain on the VMware side?
I think that's more of an optimization than the prerequisite, but is something which should go in that direction as well. But I don't think that's mandatory to go for NVMe Fabric at all. No, as far as the guest is concerned, when we are doing NVMe Fabric at the kernel layer, so it's beyond that, it's VMDKs. How you present those VMDKs to the guest, whether RDM or with VMFS or vVol, it's at the guest level. But those data stores can come from the local DAS, or it come from the remote, whether it's the SAN today or NVMe Fabric in future. So that's how you're going to consume the data stores or LUNs in the kernel. But on top of it, the model of consumption at the virtualization layer does not change. Now those VMDKs can be accessed over today. We have PV-SCSI or you have virtual NVMe. So that model will remain the way it is. So there will be no change from that point of view. Yes. Yes, that's something we are looking into it. And for us, NVMe, when we look at it, serviceability and LED management are a big area of focus as well. And we, for example, in 6.7, we have managed hot plug capability, but we want to go toward the real surprise hot plug. And that needs some heavy lifting on our end in the kernel as well as in core storage, and something we are actively looking into it to support hot plug as well as LED management. Now, does it align with the NVMe-MI, or it's something which we do it with our tier 1 OEMs independent of NVMe-MI? I think it's still TBD on that front. So I think we're running out of time, but I'll be more than happy to talk to you. But I think we're looking at a little bit broader in terms of how do we do the overall system life cycle of the system, whether it's NVMe or non-NVMe. So we are working with our tier 1 OEMs and seeing what is the right way to do it. So that's a big focus as well. We do through VUM today, VMware Updated Manager, and we are trying to go towards the next generation of that. So where we can, because a lot of that stuff is already there in VMC, how do we take that advantage and make it as part of the VMware lifecycle is where we are focusing on. Now, whether it's done through the guest operating system or it's done through the management infrastructure, I think that's something we can discuss, but that's something we have been looking very actively as we speak as well.
Thank you, Sars. Appreciate it.
Thank you.
It's a great presentation. Thank you. Our next speaker before the break is Mr. Jim Harris from Intel. He's going to talk about the storage performance development kit. So I welcome Jim.
Yeah, my name is Jim Harris. I'm a principal software engineer in Intel's data center group. My primary role is software architect and a core maintainer of the open source storage performance development kit. I'm just curious, show of hands, who's heard of SPDK before they walked into the room today? And out of those, who have actually downloaded or used it in some fashion? Okay, great. I will not read through that. Yeah, so the overview here for those that aren't familiar with SPDK is the NVMe spec. It's built for efficiency, right? You have no register reads in the I/O path. You've got multiple I/O queues to allow I/O submissions and completions to be done for multiple CPU cores in parallel without synchronization. But even with all that, the best of class kernel mode drivers, they have a non-trivial amount of software overhead. And there's a lot of really good reasons for that. Because those kernel mode drivers, they have to handle every single use case that an operating system is used for. And so it adds up. It's about 3 to 5 microseconds of software overhead per I/O. And so when we start talking about dedicated storage appliances, storage applications, where you've got SSDs that do over 500,000 IOPS, you've got 4 to 24 SSDs in a system, and you start to see media that can hit sub 10 microsecond latency, that overhead can become pretty noticeable. And so that's really where SPDK comes in. It's a set of pulled mode libraries and drivers that are really focused on NVMe, but for storage in general. So a little bit of background on this. This is an open source software project. Intel started it about 5 years ago, but it's grown significantly since then. It's a BSD licensed software project, meaning that anything that you find in SPDK can be used. It's a very permissive license. You can use it directly, make modifications, use it as reference, etc. You can go out to the project website, spdk.io, and you can get all the latest code from our GitHub repository. And I'm going to show a diagram later that kind of shows what all these building blocks are. Most of today is going to be focused on NVM Express, but there's a lot of software building blocks in here for building, general storage type appliances and applications in user space. And it's really designed around NAND and these latest generation NVM latencies. So we don't have like user space SAS drivers, user space HCI drivers. We have mechanisms to make those work with kernel mode drivers, but this is really focused around NVM Express and getting the best performance out of that. So when we look at the NVMe driver, it supports 1.3 spec compliant devices. It's all based around user space, asynchronous pulled mode operation, right? So we're not doing interrupts. We submit an IO. We don't wait for that IO. We try to go do some other work and come back later and find it. And that's really how we get the best efficiency out of the CPU. And in this case, the application actually owns all the IO queue allocations. So typically what kernel mode drivers do is they do all the allocation inside the kernel. Each core gets one queue, or maybe a set of cores have to share a queue. But in SPDK, the allocation of those queues is really up to that application. So they can allocate a queue, do the polling on a thread. They can even release it, move it to another thread, etc. And then when we look at the NVMe features that are supported, a lot of these have been supported for a little while. The main ones I'm going to call out here are controller memory buffer. So Stephen Bates from Idetacom, I know that he's here and is doing some talks tomorrow. He's pushed some patches to SPDK to support controller memory buffer, not just for submission queues, but also for data as well. So there's been work going on the Linux kernel, but we're also doing work on this for SPDK. Then we look at some of the features and capabilities that you typically want to get from a driver. So based on your application, there's a lot of things you want to be able to do. Hot plug is a big one, right? How do you do hot plug from user space? Well, it's a little bit complicated. There's actually still some kernel mode bugs that are getting worked out in the kernel, but SPDK does support hot plug and the mechanisms for being able to safely do that from user space. Things like error injection, so being able to programmatically inject errors into the NVMe IO path, either holding on to IOs so that they don't actually get submitted, to inject like reset type conditions, be able to inject different types of error types on the completion path. So open channel. Open channel is not part of the NVMe spec, but I know a number of people who are actively using SPDK on open channel SSDs today to do like user space FTLs. We have a device quirk mechanism for handling, all the quirks that you find with different SSDs from different vendors, configurable timeouts, configurable IOQ sizes, raw commands. So for if you're a vendor and you're wanting to use SPDK to do some testing, we have the raw command APIs to do vendor-specific pulled mode operations. NVMe over Fabrics, which I'm going to talk about in a little bit. Another big one that we've gotten a lot of questions on is FIO. People love using FIO on Linux to do performance testing. We do have an FIO plugin so that you can use those same scripts with SPDK. Okay, so here's some updated charts. This chart is basically showing, if we take a single Intel Xeon core, how many IOPS can we get from an NVMe system? So this is a system, we've got 22 NVMe SSDs in this, and we're basically looking at, as we go from 1, in this case we're going from 1 up to 8, how many IOs can we get out of the NVMe SSDs just using one core? So you can see with the Linux kernel driver, it gets around 450 to 500K IOPS, which is really good, and for a lot of systems, that is sufficient. But when we start to look at these storage systems where you're scaling up to many SSDs, we can see here that the SPDK driver maxes out around 3.5 million. So it can saturate 6 of the Intel P4600 SSDs. And so then, one of the questions we've gotten a lot in the past is, okay, well, this is great with one core. Well, how does it, ramp up to multiple cores? And so we can see here scales pretty linearly up to 3 Xeon cores, and then we start getting up into PCIe max bandwidths. So you can see we max out here at about 10.5 million across 4 cores, and that's actually, what's that?
Yeah.
Okay. NVMe over Fabrics Initiator. So the driver does support, just like a lot of the drivers we've heard about earlier, we have a common API for local and remote access. It's got a pluggable Fabric transport, RDMA supported currently, TCP's in progress. Just like Dave said for the Linux kernel, you'd expect to see SPDK patches once the spec becomes final. This is a big building block diagram, shows all the parts of SPDK. I'm sure this will be online for people that want to look at it in more detail. The one thing I just wanted to call out here was the NVMe over Fabrics target. So again, like Dave talked about for Linux, SPDK does have an NVMe over Fabrics target as well. Again, it's a pulled mode user space implementation. Presents SPDK block devices as namespaces. So doesn't have to be a physical NVMe namespace. We have provisions for doing logical volumes in user space, et cetera. And for this one, if you want to get some more detail, my colleague Ben Walker will be doing a talk on this tomorrow afternoon, NVMe over Fabrics scaling up with SPDK. And here's just some info if you want to get involved. I'll be here the next couple days, and if don't know how much time we have for questions today, but if you've got more questions on SPDK, I'd love to answer them. Okay.
Yeah, then let's take questions for 2-3 minutes. And yeah, so all right. Any questions on SPDK? Go ahead.
So the question was, have we tried interrupt mode in user space? So the long story is, well, let me say the short story. There are cases where dropping into an interrupt mode could be beneficial, right? If you're in a very, very low IOPS environment and you don't even want to pull on one core, then obviously dropping into an interrupt mode could be really helpful. The software libraries that were built on top of do have support for that type of thing. We don't have that built into SPDK yet, but it's something that's on the roadmap. I think what we're looking at more is looking at ways to use some of the features in the CPUs to get the system down to where it's just pulling on one core, and then even on that core reducing the frequency. From a software complexity point of view, that becomes a lot simpler. I mean, the interrupt mode can make it even lower, but it does add a lot more complexity into the application. That's a good question. Absolutely, yeah. And we build on top of the DPDK, which is basically. In fact, we used to call this project DPDK for storage. And so DPDK has support for this type of thing, to being able to drop into an interrupt mode. We just haven't really focused on enabling that for SPDK yet. But we would be very welcome to, patches or discussions to make that happen. Okay.
All right. Thank you very much. Thank you, Jim. This concludes the first part, and second part we have Brandon. Maybe you can give an introduction.